No, mic I want to use here. Pasal yesterday mic-nya jauh. I hope my mic is on here. Have you started recording, Aiman? Okay, thank you. Yes, my mic is on. Okay, so just to recap what we did yesterday, we saw that there are 5 types of d orbitals and they can be divided into 2 groups. The first group is the orbitals that sit on the axis, and the second group is the orbitals that sit between the axis. Okay? And then we also saw that when we add ligands to our metal, transition metals, the d orbitals will be split. Okay? And they're always splitted according to the group. The group of orbital that sits on the axis, and the other group is the orbitals that sit in between. It depends on the shape of the complex as well. For octahedral, the orbitals that sit on the axis will feel more repulsion, so their energy is higher. So that's why you expect the dz square and dx square y square to be at a higher level, and the rest will be at the lower level. For tetrahedral complex, the ligands do not sit on the axis, but rather they sit between the axis. So this time, it is the orbitals that sit between the axis that feels the more repulsion. Okay, so I don't draw it here, but it is the dxy, dyz, and dxz will be the one at the higher energy because more repulsion. So the idea is bigger repulsion, higher energy. Okay, that's only the introduction to why transition metals are colored. The next learning objective that we want to see is explain the origin of color in transition element complexes resulting from the absorption of light energy as an electron moves between 2 non-degenerate orbitals. Okay, so the reason for this color is due to the absorption of light. Electrons absorb light in the visible region. Only one type of light at a specific frequency or a specific wavelength. Okay? When electron absorbs this energy, when electron has energy, they can undergo what we call a promotion or excitation. That means it goes from the lower level to the higher level. Okay? So if we look at the sort of the summary, you start with a transition metal that has degenerate d orbitals, all same energy. When ligands come in, the d orbitals are now non-degenerate, or we say they are being splitted. The complex, the electrons specifically, any one of the electrons that sits in the lower energy d orbitals will absorb a frequency or a wavelength of light that matches with the gap between these 2 energy levels. Okay, it has to be the exact frequency, the exact wavelength. So when this electron, so just imagine this blue electron actually came from here. This blue electron absorbs the energy that is the same amount, the exact same amount as the gap between the 2 groups of d orbitals. It can go up. This is a process called promotion or excitation. The electron is being promoted from a low energy level to a high energy level. Okay? Okay. So here is an example. This is what you have in your notes. Another criteria that I forgot to mention is that in order for electrons to be promoted from the low energy level to the high energy level, there must be a vacancy in the high energy level. If this was full, for example, say this is occupied, of course, this electron cannot go up. Where can it sit? Okay, we're only looking at the d orbitals. We're not looking at other orbitals like 4s, 5s, 5p, and etc. We are only looking at the d orbitals. Okay, so that's one criteria. In order for electron in the lower energy, sorry, thank you, Ayman. Maybe the table color. Oh, okay. All right. Thank you. In order for electron in the lower energy level, lower energy orbital, to be promoted or excited to the higher energy orbital, there must be, of course, there must be a room or a space. There must be a vacancy in the higher energy orbital. So this energy needed to promote one electron on actually promotion, you will only absorb one type of light at a specific frequency or wavelength. Okay, too low energy, you will not reach the high energy orbital. Too high, you will miss it. Okay, so it has to be the exact amount of energy. So later I will teach you the formula, but thankfully for your syllabus, you don't have to work out. Okay, you're only going to look at it qualitatively, not quantitatively. So as mentioned earlier, the gap between the high energy and the low energy d orbital is represented as delta E. Sometimes it's called the splitting energy. Okay? So it takes 180 kilojoules per mole of energy to promote or excite the electron from the lower energy level. It can be any electron actually, right? Any one out of the 6. And then when you promote it to the higher energy level, it can sit anywhere that has a vacancy or that has a space. Okay, so what does that have to do with colors? The energy needed for this excitation or promotion is supplied from the visible light. Okay, the light energy being absorbed. So the color that you see is actually the complementary color. Okay, I'll talk about complementary color later. So the difference between the splitted d orbitals, delta E, is the energy absorbed by the electron. This energy is usually within the visible spectrum. So whether you absorb red, red light, blue light, yellow light, as long as it's in the visible region. Okay. To work out the frequency of the energy required to promote or excite the electron, you use the expression delta E equals to hv, where h is a Planck's constant, it's a number, it's a constant, it's given in your data booklet, 6.63 times 10 to the power of negative 34 joules second. V is your frequency. Okay, so be careful if the question gives you a wavelength. V is actually the frequency, but thankfully you don't have to I don't remember if there's a question that asks you to work out. So far, I have not seen it. Okay? So V is the frequency of light. In second to the power of minus 1 or hertz. Okay? Next. The light energy that is being absorbed by the electron for the promotion to happen, okay? The color that we see will be the complementary color to the one that is absorbed. So if you read here, 180 kilojoules per mole of energy, delta E for copper. If we work it out, all right, we should get a frequency that represents the red light. Okay, frequency of red light is, I don't have the number, okay, but it should match the frequency of a red light. However, the color that is being transmitted by the complex ion is the complementary. The complementary is the opposite color in the color wheel. So you see here, Cu2 plus absorbs red light, uses that energy to promote or excite its electron. However, the color that is being transmitted or given out is the complementary color, which is light blue. So that means if copper 2 plus shows a blue solution, this complex does not absorb blue color. Okay? So they absorb the color that is, I wouldn't call it opposite, but we call it complementary. Another example, CuCl4 2 minus, yellow solution, right? So if you look at yellow solution here, that means that complex ion have absorbed frequency of light that matches the delta E, of course, and that's the blue color, blue light, all right? So CuCl4 2 minus will absorb blue light to excite its electron. The color that it gives out will be yellow. Okay? So that is basically how you explain origin of colors. Okay, so let's just read this again. The red light will be absorbed, but the complementary color will be transmitted. Sometimes they use the word observed because that's the color that we see. Okay, don't confuse observed and absorbed. Absorbed means taken in. Observed means we see the color. So that's how copper 2 plus shows a pale blue solution, but because it absorbs the energy of a red light or the frequency of a red light. This is just to show different um, color or different lights with their respective wavelength and frequency. Um, the numbers I did not put because I think we have not used it for calculation of your delta E, right? But what I want to point out here is that light that has a high frequency would have a shorter wavelength, which I'm sure you know this already from physics. Lights with low frequency would have a bigger wavelength. Okay? Right. So the important point here is that the color transmitted or observed of the complex ion is usually the complementary to the light frequency of light being absorbed. Sometimes they give you data in the question, okay, of the complementary color, or they give you the frequency number or the wavelength numbers. so you can use the data. Okay, later on, I think after this, I will stop with theory first before we move on to the next part of transition metals. We'll do some questions. Okay. Okay, so if the most common question in the exam is to explain the origin of colors in complex ions, or they will say, why is CuH2O6 2 plus blue colored? Okay, so the question, sometimes they try to change it, tweak it, but the answer is always the same, right? We're going to bring in together all the concepts that we have learned from yesterday into 4 points. Okay, the question is usually worth 3 or 4 marks. So the first point, we will start with the D subshells are being splitted into 2 sets of different energy level, or as you know, it is called non-degenerate. Degenerate, cannot spell. And then light is being absorbed, that corresponds to the delta E. It has to match the size of the gap. This light being absorbed is in the form of energy. So this energy is used to promote or to excite the electron from the lower d orbitals to the higher d orbitals. And the color we see is the complementary to the light that is being absorbed. All that, all the things that we have covered from yesterday, just to explain the origin of colors. Okay? So you can copy this down. Hmm? Mm-hmm. Uh-huh. Yes. Delta E 180 kilojoules per mole. If you want to know what color, if you want to work out the frequency of the red light, you have to use HV or HF. Okay? So you work out the frequency. And you have to know the number of moles also because it's in kilojoules per mole. Yeah. So that 180 kilojoules per mole is not the frequency of light, it's the size of the delta E. If you want to know the frequency of light, you need to do further calculation using the expression delta E equals to HF or HV. Okay, done? Oh, madam. So these are the explanation for complex ions that have colors. What about for complex ions that are either colorless or white? Okay, so that means which one of these points are not happening in this colorless complex ions? Okay, which we are going to look at after this. Cadmium and zinc, these two are D block elements, but they're not transition metals. Okay, so these are good examples of why they don't fit or they're not cut out to be transition metals, because the criteria for transition metals is one, they need to have more than one ion, like copper plus, copper 2 plus, Fe2 plus, Fe3 plus. they have more than one oxidation state, I mean. And secondly, their ions must be colored. Whereas for scandium and zinc, their ions are not colored. They only have one ion, which is Sc3 plus for scandium. Zinc is zinc 2 plus, and yet they're both colorless. Okay, so we're going to look at uh, the complex ions that are colorless first. Okay, here example, scandium. Scandium has an electronic configuration of 4s2 3d1. Scandium ion Sc3 plus means we lose the 2 electrons from 4s and 1 electron from 3d. So Sc3 plus will have an electronic configuration of 3d0. Okay? The d orbitals are being splitted. That's okay. However, the problem here is that there is no electron to be promoted. So if there's no electron to be promoted, there's no absorption in light, no light being transmitted, no color being transmitted. Simple as that. Okay? For zinc, zinc atom, the electronic configuration is 4s2 3d10. Zinc ion, zinc 2 plus means you lose the 2 electrons from the 4s orbital. So the electronic configuration is 3d10. Notice that I'm only interested in the d orbitals, okay, because the color is due to the absorption of that, the excitation or the promotion of the electrons. 3d10, I have d splitting, d orbitals are splitting. I have electrons. My electron can absorb light, energy, frequency of light. However, there is no space or no vacancy for the electron in the lower energy orbital to move to the higher energy orbital. Okay, so of course, since there's no space, promotion cannot happen, excitation cannot happen, so transmission doesn't happen as well. No color, colorless. Okay. Here's example of copper you have seen already. After the d orbitals are being splitted, one electron from the lower energy level can be excited to the higher energy level. There is a vacancy, there is a space. So when it absorbs the light and use the energy to promote or excite the electron, they then give out or they transmit color that is complementary to the absorbed frequency. Titanium Ti3 plus, it has an electronic configuration of 3d1. This electron in the lower energy level can be excited to the higher energy level. So that's why it appears violet purple. Okay? So that explains the scandium and zinc, why they are colorless. You have this in your notes at the bottom page of 17. I think this would be helpful if you just draw out the electronic configuration to show why electron promotion cannot happen. There's no electron in the 3d orbitals of scandium 3 plus, whereas in the 3d orbitals of the zinc 2 plus, the orbitals are fully occupied. Electrons cannot be promoted. So 3d0 is empty, 3d10 is full. What time we finish, 10:15, huh? Okay, we'll have plenty of time. Oh, we still have another one, huh? Page 18. So that's what you would write if the question asks, why is copper 2 plus blue color, or why is it a blue solution? Okay. However, how do we explain copper 2 plus with 6 water molecules, that is a blue solution, and copper 2 plus with 4 chloride ions, which is a yellow solution? They're both the same transition metal. However, the color is different. Okay. The major difference between these two is the ligands, the type of ligands. One is a water molecule, and the other one is chloride ligands. Okay, can we move on? So next, we're going to look at the factors affecting delta E qualitatively, the effects of different ligands on delta E. So if you change ligands, the frequency of light absorbed will also be changed, and hence the complementary color will also be different. Right, so I will just talk about these factors affecting delta E, but the one that we're interested in is actually just the type of ligands. Okay. Nature of transition metal ion, of course, copper 2 plus is blue, cobalt 2 plus is pink. That's already an example of why different metals will give different colors. Oxidation state in like Fe2 plus and Fe3 plus. Fe2 plus is green solution, Fe3 plus is brown. The nature of the ligands, which is what we're going to look at after this. When you have water molecule as your ligand and when you have ammonia molecule as your ligand, of course, your delta E will change. The coordination of the metal ion, same thing. This goes together with the nature of your ligands, whether it's an octahedral complex or whether it's a tetrahedral complex. But for your syllabus, we're only interested in the ligands, okay? So I will talk about ligands. Can I move on? Because I see you're copying things down. Okay, so one of the factors that affect the exact energy difference, delta E, is the identity of the ligand. So what does ligand do that affects the change in color? Actually, when you change the ligands, the splitting energy will also change. The delta E will also change. Some ligands will cause a small delta E. Some ligands will cause a big delta E. Thankfully, you do not have to explain this. All you have to remember is that different ligands will change the size of delta E. So if you change the size of delta E, knowing that delta E is equals to H times frequency, if delta E changes, the frequency of light that you absorb will also change. That's why you see different color. Okay? Right. Changing a ligand or changing the coordination number will alter the energy split between the d orbitals. That means the delta E will be changed. Therefore, the frequency of light absorbed will also be different. Okay, here's an example. When we add ammonia, aqueous ammonia to copper 2 plus until excess. So copper 2 plus is a pale blue, light blue solution. Upon the addition of ammonia, drop by drop, you will first observe precipitate, which is your copper hydroxide, and then in excess, the precipitate will dissolve to give out a deep blue or dark blue solution. So what happens is, because water as a ligand will only cause your delta E to split by a small amount. Okay, we're just looking at it qualitatively, right? We don't have to look at the numbers. Whereas ammonia, now that you have ammonia in your complex, will cause the splitting energy to be bigger. Okay, so that's why the color also changes, because the frequency of light being absorbed in order for promotion of electrons to happen will also be different. Okay? This is the trend of ligands that cause The amount of splitting that can be caused by these different ligands. Chloride has the smallest splitting. That means the delta E for complex ions with chloride ligands will be the smallest relatively, and cyanide ions will be the biggest delta E. Okay, you don't have to worry about the numbers. So if the question asks, explain why Fe2 plus is green, Fe3 plus is orange, that means, eh, sorry, that's not ligand. Sorry. Explain why copper 2 plus is blue solution and copper with 4 chlorides ligands is a yellow solution. The answer is this. First point, well, we changed the ligands, right? The ligands is being replaced. The H2O ligands is being replaced by the chloride ligands. Therefore, the delta E is also altered, or we say the delta is different. Delta E is different, and so different frequency or wavelength of light is absorbed. Yes, it's 1/. 1/, right? 1/, yeah. Frequency is 1/, wavelength. Well, uh, what's the full formula? Physics. Apa? F lambda. V is equals to F lambda. What's V? Okay, yeah, something like that lah. Basically, I know that they are inversely proportional saja. So frequency is equals to 1/, well, not equals to, but proportional to 1/, wavelength. Yeah, and yeah, if you want to know, to work out, you can ask the physicists. Okay, Balam. That's it. That's it for today. Okay, so that covers the explanation of colors in transition metal complexes. So everyone is here, including Hazwan, who is joining us virtually. So don't forget to update me, yeah, if your parents want to come see me. So you 4.1. Okay, if you're done, you can pack up and go. You 5.1, 16 out of 17 has one online. Aiman, can you help me stop the recording or the meeting altogether?
Sekiranya kalau a question,
Mhm.
dia bagi the energy, so
Mhm.
this is E kan tu, E delta E, then kami sekiranya tanyalah what color will be seen, sekiranya. So we need to know the
Frequency, yes.
So frekuensinya ada value betul?
Yes, frequency ada value.
Because ini high low, tapi
Yeah,
ada value.
there will be a value for the frequency. Yes, correct. Thank you, Aiman.